Recently, DeepSeek models caused a wave of disruption in the high-tech market, leading to significant crashes in the market values of major players. For example, like NVIDIA. About $1 trillion were wiped out of the AI market and related high-tech market as well. And for NVIDIA, it was about $600 billion were wiped out from NVIDIA alone. This was triggered by DeepSeek, a Chinese startup, when it recently has revealed its new model, DeepSeek-R1, which is claimed to be more efficient and cost-effective than the current models on the market. The technical report of the model was published on Archive, which is not the conventional or the typical way of publishing things about AI. This report contains detailed explanations about the model and the training process involved as well. Moreover, the base model was released as an open source model with an MIT license. And this is a significant step in the AI development because such license will allow developers to refine the model, build applications on top of it, and also commercialize it. Releasing the model in an open source form is not the first step to be done by DeepSeek. IBM has also released several AI foundation models as open source models like Granite, for example, which are specialized models or have been fine-tuned for specific applications or tasks like weather forecasting, time series forecasting, code analysis, documentations, and more. DeepSeek was a significant milestone in the AI market, not only because it was an open source, because of the way that the DeepSeek team has claimed in the fine-tuning and training the model itself. They have enhanced the algorithmic way of training and fine-tuning the model, in which made the model applicable and could be trained on less intensive computational resources. Let's discuss it in this video. DeepSeek was a significant milestone in the AI world, not only because it was an open source, because the DeepSeek team has claimed a profound way of and innovative way of training the model and also pre-designed the architecture involved in the training process, which demanded less computational resources and becoming more cost efficient. And this brings us to the question of this video. How models like DeepSeek-R1 and other AI foundation models can help accelerating quantum simulations like chemistry simulations or physics simulations, enabling simulations of larger scale systems and also solving complicated and complex physics problems, and perhaps paving the way for the next leap in physics intelligence, or what I can call quantum intelligence. Moreover, how open source models will drive innovation in the future and foster industries to build applications on top of these models. Could we use LLM-based models to assist the design of chemistry and physics simulations or not? We are about to find out in this video. So the recent release of DeepSeek-R1 has caused a huge disturbance and also disruption in the market and disrupted the race towards what we call artificial general intelligence or AGI. It has shaken the way that we believe to be the de facto standard in the AI models, that AI models need to be trained on massive data and powerful machines. And that remarkable results can only be achieved with multi-billion-dollar investments, ignoring to some extent genuine innovations in methodologies involved in the training and in the design. This kind of belief makes it hard for small companies like, for example, and startups like us, for example, to compete with major players in the market. DeepSeek also has prioritized the resource efficiency more than just spending on expensive data centers. And furthermore, DeepSeek was published as an open source model along with 6 small variants ranging from 1.5 billion to 70 billion parameters with an MIT license, which, as I have said in the beginning, it allows developers to refine it, build applications on top of it, and also potentially commercialize it. I have made a video on how companies can make money with open source software titled "Can Startups Still Make Money with Open Source Software in 2024?" You can check it out here. I will leave the link on the screen and below in the description of the video. It's also worth to mention that the founder of DeepSeek, Liang Wenfeng, is about 39 years old, also backs the idea of open source community, and this is why he made and offered DeepSeek-R1 as an open source software He believes that AI is not only about investments, but also about an innovative way of creating models with fewer computing resources. Hence, the DeepSeek team developed different efficient ways to make the model learn faster, but also more efficiently from smaller datasets, especially by employing reinforcement learning techniques and multi-stage trainings in the process. The company has released a free AI assistant, DeepSeek Assistant, which surpassed ChatGPT as a top free app on the US App Store. And the market disruption caused by DeepSeek R1 has caused significant drop in the stock prices of major tech companies like NVIDIA, OpenAI, and Google, mainly because it made many investors question the multi-billion-dollar investments in AI and whether these investments were already really necessary to achieve remarkable results or not. To understand how algorithmic design works, let's take a simple example of numerical integrations. You can, for example, use a simple method like trapezoidal rule to integrate a function. To achieve convergence, you might need hundreds or presumably thousands of points in order to achieve a numerical value that's close to the analytical solution. To achieve convergence, then you might need really a lot of points. However, you can use an efficient procedure for integration like the quadrature method, which is more efficient and accurate than the trapezoidal rule, provided that the function itself is smooth and you can find out the pattern of the function. If you know or you are able to find the pattern or the right pattern of the function, you can use this quadrature method to integrate the function, which makes the integration faster and more accurate, and you can always perform the integration using only few points. Another example is in quantum chemistry. If you want to interpolate a potential energy surface between two molecules, for example, there are potentially some functions that you can use to interpolate efficiently without the need for large data sets, providing that these functions also probe the symmetry of these potential energy surfaces. So you don't need a lot of points, you need some points or fewer points, and then with the right functions you can perform or achieve a good interpolation. This is where the algorithmic design of the model comes into play. Similarly, the DeepSeek team used alternative smart approaches to reduce the cost of training the model and train it on even older processors in a much shorter time than the current models on the market, for example, have consumed in their trainings. And whether the reported numbers by the Chinese are right or not, it shows us that how these algorithmic developments and innovations can really reduce the cost substantially than, for example, competitors or rivals in the market. So this brings me to the point: how can AI models help accelerating quantum simulations and pave the way for the next leap in physics intelligence or quantum intelligence? If you have quantum data, for example, you need to think about the architecture of the model, how you can probe the underlying patterns in this data. A good architecture, for example, can make the model learn faster and more efficiently from smaller data sets. This means that you need a kernel that is tuned to the type of data you have and presumably probes some of the hidden patterns in the data. To achieve this, you need to consider the architecture of the model first before training a full model, which might be costly to train. Hence, when we use physics-inspired kernels, like a system of basis functions that are inspired by physics of the system, we can train the model to understand the system in a very efficient way, and even predict the future instances of this system and simulate the system more efficiently. In that sense, we can call it physics intelligence or quantum intelligence. This is something that cannot be achieved easily using the base architectures of, for example, of generative AI models or text-based encoding models. In chemistry simulations, we are often required to describe the system in a form of a Hamiltonian. This is a mathematical formula that includes the kinetic and the potential operators about a molecule or a given molecular system. Sometimes the Hamiltonian is not known and we need to derive it. Such a derivation can be, in most of cases, very complicated, and it takes a lot of time to find out and prove. Typically, to ask AI models like GPT-based models or DeepSeek even to write code or to solve or create a physics simulation, Such models leverage the knowledge that have been gathered from codes already published on the internet and tries to fill in the gaps. But what if the codes are not available? What if the Hamiltonian is not known? If we can create a model that can learn the Hamiltonian and derive it from the data, or predict the Hamiltonian for larger or given systems using the knowledge that have been inherited from the known Hamiltonians of smaller systems, for example, and the ways in which they have been derived, this could be a game changer in the field of quantum chemistry, quantum computing, and physics in general. There are several works trying to leverage AI-based architectures like transformer architecture and the GPT models to solve quantum chemistry problems. However, such models require a large amount of conversion of chemical data and the physical equations to text-based encoding, which is not an efficient process because you need to find a way and map the thinking of the problem on the encoder or the transformer that's used to decode the reasoning and the relations between words in the text. So it's not obvious how to use such models to solve quantum chemistry problems. This is where models like DeepSeek R1 can be a game changer because they broke the status quo and proved that we need more innovative solutions to benefit from AI capabilities in physics and chemistry simulations. By working on the algorithmic design of the model, which can adapt to the physics of the problem, we can achieve quantum or physics intelligence that can solve complex physics problems and enable sophisticated large-scale chemistry simulations. And therefore, such models could be potentially understand the system and simulate even larger or different systems. This could be a great leap in the field of quantum simulations and paves the way for physics and quantum intelligence. Recently, NVIDIA CEO put forward the universal function approximator concept, which leverages the universal function approximation theorem. In this concept, you can just have an AI model that's trained on inputs and outputs of the algorithm, and the model will try to approximate the algorithm itself just by training or having enough training on the inputs and outputs. If you come to chemistry and you have a quantum chemistry or quantum computing algorithm, it's not obvious most of the time how the inputs are related to the outputs. Such models or such algorithms are composed of many and several steps in between. So the idea to create a way to approximate an algorithm by simply training a function on the input and the output of the algorithm might not be easy or not in general applicable in chemistry or physics simulations. However, with the physics-inspired kernels, there is a possibility to train the models to understand the system, predict the future instance of the system, and also simulate the dynamics of the system more efficiently because they learn about the physics and they can predict the physics as well. So this is a quick input from me. If you have a use case or you would like to try AI model for your chemistry or physics inspired applications, don't hesitate to feel free to reach to us on email and LinkedIn. Until then, see you next time.